We might not notice, but tremendous technology and mind-boggling science constantly surround us in the products we use every day. Behind their practical use lurk hidden histories, dramatic discoveries, and awesome experiments. They are Wicked Inventions. Coming up, beer. We'll find out why drinking beer used to be healthier than drinking water. Liquid crystal displays. We reveal the mysterious light-bending substance that lurks behind your computer display. Glass. The journey from volcano to high-class drinking vessel. We reveal the surprising science and amazing manufacture behind these wicked inventions. Beer brewing is one of the oldest man-made processes that we have, and it's certainly one of the oldest prepared beverages. Amongst the ancient city of Babylon in Mesopotamia and the pyramids of ancient Egypt, men began to cultivate barley as early as 6000 BC. After barley loaves were left out in the rain, they began to ferment. Not wanting to waste the crop, the brew was flavoured with rich honey and drank. Beer began to reach Europe in around 3000 BC and was brewed by Celtic and Germanic tribes on a domestic level.
Beer was deemed much more safe to drink than water. So water in those days was a bit of Russian roulette when you drank it. If you think about the sewage system, it's no surprise that it can then contaminate the water that they actually were drinking from. At least it had been through a process of heating, perhaps there was a bit of alcohol in it, which would help neutralise some pathogens. This would, to some extent, clean the water, make it more safe, certainly more safe than just drinking straight water.
With the help of the Industrial Revolution in the 18th century, beer was able to be produced on a huge scale, and the beer industry continues to thrive today. An estimated 35 billion gallons of beer are sold every year. That's a lot of trips to the pub. Beer certainly has been on quite the journey, but just how is it made? Producing almost 8 million pints a year, award-winning Purity Brewing Company certainly know how to create the perfect pint.
Purity Brewing was set up in 2005 by Paul Halsey and Jim Minkin, and their vision was to refresh the traditional cask ale market, if you like, by brewing really vital, fresh beers with an ethical ethos. At the moment, we're brewing about 500 brewers' barrels a week. Each batch that we brew is the equivalent of about 12,000 pints.
The process starts with the marisotta, a variety of malted barley grain which comes from the 15-ton storage silos. Depending on the particular recipe being brewed, other specially chosen malts are added to help give the beer its distinctive flavour.
So alongside the marisotta, which makes 80–90% of the grain bill, we use speciality malts which give the beer different flavours and tastes, aromas and colour. And we think there are around 150 different kinds of speciality malt available to the brewer as well, so mixing those up gives you a huge potential for a variety of different beers.
The malts are milled and then fed through into a mash kettle. Here the crushed malted barley is added to hot water to create a sweet porridge-like mixture. This process releases the sugars from the barley to allow the yeast to feed and produce alcohol. The sweet porridge-like mix is then filtered in the Lauterton to remove all the grain and husks. The clear liquid known as wort that remains is then pumped back to the original dual-purpose kettle and then heated with the first round of hops.
Hops are a product that brewers have been using for about 500 or 600 years. By adding hops, what you do is you add mouth bitterness. We boil away for about an hour, which incorporates the hop pellets. It reduces and condenses the sugars. It also clears any bacteria that are latent in the cereal grain or anywhere within the wort.
The spent hops are removed by separating them from the boiling wort in the whirlpool. By spinning the wort, the centrifugal force pushes the hop compounds and any proteins that may have formed out of the vessel. Throughout the whole process, checks are made to ensure the quality of the beer, examining the alcoholic volume, colour, strength of the yeast, and, most importantly, the taste. Every day, more than 50 checks are made. The next step is adding the aroma hops.
That's a batch of the hop leaves, hop cones, chosen by the brewer to add different aromas and flavours. So notes of citrus, pine, fruit, all these different things can be derived from hops. And there are maybe 250 different kinds of hop variety that are currently being used in the brewing trade, which goes to show the potential for all those types of beers that are out there. Once we've got the hop wort ready, we then push it through the hop rocket, which has got the hop leaves in it. That extracts all those essential oils out, gives it the aroma and flavour, and the wort just falls through it very quickly. It doesn't sit and steep.
The hot wort must be brought down to a suitable temperature for fermentation before yeast is added.
Final part of the journey to the fermentation vessels is actually through a heat exchange, because what we need to do is cool down that wort that's been boiling away for an hour, but we also need to generate hot water for the next brew as well. The hot water going out of the wort passes by cold water coming into the business. The hot wort is cooled down, the cold water coming in is heated up, transmitting that heat from one to the other.
The cooled wort is transferred to a fermentation tank and yeast is then added. The fermentation tanks are where the wort becomes what we recognise as beer. How long it stays in the tank depends on the type of beer being brewed. For most ales, the fermentation stage typically takes around 3 days. Once the beer is ready, the casks are prepared. They are cleaned immediately before use to ensure hygiene standards.
That process for us is really important because it has to be a clean process. All we want to go into those barrels is our beer. So rather than just jet washing out the empty barrels, what we then do in the brew house is we give them a caustic rinse, steam and pressure clean as well through a clever bit of kit.
The keystone plug is fitted before the casks are filled with beer and the shive bung added to seal the beer in. The casks are given a rinse, labelled and prepared for dispatch before being loaded up and sent to pubs and restaurants to bring customers the ultimate pint. With a history dating back many thousands of years, beer is truly a wicked invention. LCDs or liquid crystal displays have been busy displaying everything from the time to the latest soap opera. But the substance at the heart of this technology is, well, a little strange. Traditionally, we are taught that there are 3 states of matter: solid, liquid and gas. But in 1888, an Austrian chemist named Friedrich Reinitzer discovered a material that he couldn't fit into these definitions. He had discovered liquid crystals, which he found inhabited another state entirely, somewhere in between liquids and solids. With the help of a couple of colleagues, Reinitzer's investigations found that this new substance had some intriguing properties.
Back in the 1880s, people understood that certain materials, depending on the temperature range, had different refraction properties, that the light, when it went through, changed colours and changed and split out, and it's just a bit different and a bit odd. But no one really understood what to do with it. And since then, a lot of people characterised a couple hundred more different materials which could do this particular property. But there's no use for them.
Unlike solids, which have their atoms packed tightly in a neat crystalline lattice, or liquids, where the atoms lack the order of a solid, liquid crystals were discovered to exist with a strange combination of both, some of the order of a solid and some of the fluidity of a liquid. It was also found that liquid crystals had many substates, with the 2 most important being pneumatic, where the molecules can move and shuffle past each other while all facing the same general direction, and smectic, which sees the molecules form layers that can slide along each other but do not mix. The pneumatic phase is the key to why liquid crystals are so useful for manipulating light. In this phase, the liquid crystals adopt a twisted up structure, but it was also found that when you apply electricity to them, they straighten out again. This behaviour explains the odd refracting light observed by Reinitzer and his colleagues, and means that liquid crystals could be used to control light, like a polarising filter.
A polarising filter works because what it actually does is it takes light and allows only light in certain forms to pass through. Light, if it's shone on water, will scatter and it comes back at different angles. Imagine you have a series of dominoes. As they're falling over, they're at different angles. Water essentially comes off light at all different angles at you. And if you then have a slit that says only vertical dominoes can come through, only vertical light can come through. That's what you need for a polarizing filter to work. It has to be able to say only this lot, which does mean it actually cuts out quite a lot of the light. But the benefit of it is that you get a very consistent picture of whatever you're seeing, and if you rotate it, depending on how you rotate it, you'll see different properties of the water. You'll be able to see through the water, or you'll see the glare on top of the water. And so as you use it, it's very excellent in photography because it actually cuts down the glare.
Liquid crystals would have remained a scientific curiosity if it wasn't for the rapid development in electronics during the 1940s and their continued miniaturization into the post-war period.
So in the 1950s and 1960s, people began to experiment with what electronics could do to affect the properties of these liquid crystals. So under certain conditions, you could actually change the refracting properties to be either, say, dark or light, which is where the first LCD displays came from. So you would change, with the power, you would change the colour of the system and it would become black. At which point, it's opaque, you can't see it through it. If you shape those correctly, you get numbers. Then with electronics, you can then count down numbers, and so you suddenly have an alarm clock, or a clock of a kind.
These original reflective liquid crystal displays were very similar to the LCD display you find on a digital watch today. So, how do they actually work? First, we need to understand light a little better. Light is made out of particles called photons. These photons travel at the speed of light. While moving, a photon vibrates in a plane that is perpendicular to its direction, but within this plane, the vibration direction is random for normal or non-polarized light. Liquid crystal materials emit no light themselves. A mirror at the rear of the device reflects light back through a series of layers, which include polarizing filters, the twisted liquid crystals, and an electrode. The first polarizing filter allows only light vibrating in a vertical direction to come through. The twisted liquid crystal layer then rotates the light by 90 degrees so that it is vibrating horizontally. The second, horizontally orientated polarizing filter allows this light through, so we have no image, just light. To make the numbers appear, small electrodes charge the liquid crystals and make them untwist, so that the vertically vibrating light passes through unchanged. Because the second polarizing filter is horizontally aligned, the light is blocked. This creates the black blocks that appear on the display to form the numbers. LCDs were light and power efficient, and in the 1980s, the first LCD televisions were developed, with high-definition LCD televisions being commercially available in the 2000s. Although based on the same principle as the earlier reflective LCD design, television monitors needed far more sophisticated technology to cope with the 2 million pixels needed to view a high-definition picture. To complicate things further, each pixel also needed to be subdivided into red, green and blue subpixels to cope with the colour.
So what you have is each pixel has a red, green and a blue, which for light helps us to make it white and all the colours in between. And you need to be able to turn them on and make them transparent to light, so that say the blue comes through, or turn them off so the blue doesn't come through, or varying combinations of in between. Liquid crystals on their own do not emit light, so you need to have a power source behind it. Normal LCD displays work with, essentially, a modernised version of a compact fluorescent light bulb. It sits at the bottom, shoots light up, and then that light that's shot up is then filtered by the LCDs, and those LCDs give you the colours you were looking in the right spots, which then we interpret as humans as a picture.
This technology means that today's HD LCD screens have a palette of 16.8 million colours, enough to guarantee even the crispest of images. Liquid crystal displays, truly a wicked invention. Can we create a super stealthy private computer screen? We're going to need an old monitor, a polarizing filter sheet, an old pair of 3D glasses, a sharp craft knife, some scissors, a pen, and a prying tool. We gently remove the plastic front surround and polarizing filter from the computer screen. If we turn the screen on, we just get a big bright light. Remove the lenses from the 3D glasses and replace them with sections cut from the polarizing filter. put the glasses on and the big white screen is now transformed into a normal LCD that only you can view. As we saw earlier, polarizing filters are needed to control the light that we see emitting from the screen. By taking away the LCD's final filter, we have rendered it unusable with light emitting in all directions. By creating a replacement filter on the glasses, the polarizing layer gives back that control of the light between the monitor and your eyeball. The only difference is that this happens really close to your eye and not on the monitor itself. Can we create a super stealthy private computer screen? Yes, we can. Wicked challenge smashed. Glass has been a part of human history since our earliest origins. There is evidence to suggest that naturally formed glass, created by the intense heat of volcanoes melting sand, was first used as spear tips. It wasn't until 1500 BC that glass would be used as a hollow container, as it is today. This early glass wasn't the clear product we see today though. Impurities in the raw material caused the glass to be coloured. In the time of the Romans, glass making was considered an art form, and glass was a rare luxury item. Because of this, the secrets of glass blowing were closely guarded, and it wasn't until the fall of the Roman Empire that the craft spread throughout Europe and the Middle East. The traditional glass-blowing techniques of Roman times remained almost unchanged for centuries and are very similar even today. However, a major milestone in the history of glassmaking occurred in the 17th century in Britain as businessman George Ravenscroft developed and invented lead glass. By introducing lead to the raw material, he found that the glass became much clearer. It was softer and easier to decorate. As well as this, it was much more shiny, and its refractive qualities caused it to resemble beautiful crystal when cut.
And this is where the sort of skills involved with cut glass really improved. And English and Irish cut glass was famous and well known. And they were taken to the States in the 18th century. And then they started to sort of develop cut glass sort of later in the 18th century. And all those developments meant that it was easier and cheaper to some degree to make really fine, very, very ornate cut glass.
Without this leap in glass-making technology, we wouldn't have the lenses used in optics, microscopes, or astronomical telescopes. Who knows, perhaps without George Ravenscroft's lead glass, we may never have journeyed to the stars. After this, the modern glass industry became a real force. Decorative crystal glass became hugely popular and a sign of status and wealth. Cut crystal glass is today as much as an art form as it was in Roman times, with highly skilled and experienced glass blowers and cutters creating beautiful decorative creations and techniques that still remain unchanged for centuries. From the depths of a volcano through the Roman Empire and beyond, glass truly has been on one amazing journey. Based in the beautiful surroundings of Ulverston in England's Lake District, Cumbria Crystal are Britain's last remaining handcrafted luxury crystal glass manufacturer.
We were formed 40 years ago by Lord and Lady Cavendish, who are local landowners. They brought glassmakers from Stourbridge, the heart of England and one of the historical centres of English glassmaking, and brought them to the company up here, and the company's been running ever since.
The glass-making process begins with blowing. Teams of either 3 or 5 highly skilled glassmakers work together in what appears to be a dance, gathering glass out of the furnace at a temperature of 1200 degrees Celsius. When making stemware, the wine bowl is blown into a graphite or steel mould by the wine blower and then handed to the servitor, who casts on the stem and the foot in a traditional factory technique rarely seen today. He then shapes the stem and foot using wooden and metal tools, which haven't changed in design for centuries. With what seems a sleight of hand, a wine glass appears and is given to the apprentice, who cracks it off the blowing iron and places it into a large kiln, called the annealing leer. Here, the glass slowly cools and is de-stressed overnight with the rest of the day's production. The glass is then taken from the leer and moved on to the processing stage.
The first part of that processing stage is trapping it upside down in a machine, scoring it with a glass cutter, and then putting a little flame around the line that has been scored around the glass. This separates the bit of glass which is wasted, we don't need that. That falls off and again is recycled. And then that piece of glass is passed through to another machine which has 2 diamond discs that rotate underneath it. By rotating it there, we make sure that we remove any sharp edges and we grind the glass down to the exact height we require. Next, edges are ground off to take away any sharp or any minute chips.
After the rim has been ground down, it seems to have a frosted effect. To remove the frosting, the glass is then put into an edge melting machine. Here, 3 different temperature flames are aimed at only the rim of the glass, which, in effect, smooths out the rim and gives it a shine to match the rest of the glass. From here, the glass is put into another kiln that heats it up to 470 degrees Celsius, and then it is slowly cooled again. This removes any internal stresses the glass may have picked up during the processing stage. Once this has been completed, 1 or 2 days later, the glass moves on to be quality checked for any slight defects such as bubbles in the glass. It is at this point that a decision can be made as to which glass suits which crystal cut design. Minor imperfections can often be removed during the cutting stage, so this quality check is very important. The glass is then marked up using semi-permanent pens. These marks act as a guide for the cutters in the next stage of production. Real magic happens in the cutting room, where Cumbria Crystal's artisan cutters still use a traditional 2-stage process of roughing and smoothing. The first cut is made on a diamond wheel and is then smoothed on a sandstone wheel. This is a time-consuming technique that is rarely used now, but this method achieves a sharpness and quality of finish unrivaled in the industry, and which cannot be replicated by machine. Cumbria Crystal's cutters are skilled in many different cutting techniques, including mitre, diamond, flute, flat, and thumbprint cuts of both fine and strong detail, working with both contemporary and traditional designs. The crystal is then polished with a traditional acid polishing technique, which brings out the brilliance and retains the sharpness of the cuts. After it is acid polished, the crystal is moved on to the final grading stage. All the crystal is graded at stages during production, and then a final inspection before packing ensures high quality standards are maintained and that customers receive the very best quality of crystal. Each piece is carefully wrapped and packaged professionally for delivery, ready to sparkle in the cabinets and dining rooms of some of the world's finest establishments.
In the luxury crystal world, Cumbria Crystal is very, very well known. We retail in the top retail stores around the world, and the people who collect Cumbria Crystal are members of royal families, the super rich, and people who really appreciate craftsmanship and British tradition.
Now that's a crystal clear, wicked invention. So, there you have it, a dash through the hidden history, super science, and amazing manufacture of products that you use every day, but have never realised their amazing backgrounds. Beer, liquid crystal displays, and glass. All wicked inventions.